let me get right into it. This is a picture taken by the James Webb Space Telescope, which was launched 3 years ago. And this is a famous picture, which shows a number of things. And we will be talking about the James Webb a lot because it is really transformational. It is really changing what we're doing in astronomy and what we know about the universe. What you can see here, well, the most obvious thing you see are these things with the big rays on them. Those are actually nearby stars. They're not so interesting to us. For us, the interesting stuff is the faint stuff, galaxies like this. These little points of light, which are some of the most distant things in the whole universe. That's what James Webb is allowing us to do. Here is the telescope. For size, you can see these people here. It's 6 meters across. And it's made in these pieces here. Partly because there's no rocket big enough to launch anything that's 6 meters across. It had to be folded up and then unfolded in space. And those are also adjustable to get the best focus as possible. So that's the James Webb Telescope. And George Rinke made a nice comment. Astronomy is one of the few good news gets above the fold in the papers. This was a pretty famous picture a few years ago already. And you can actually give you a secret. You can tell if it's a James Webb photograph because these star images have 6 rays, which reflects the hexagonal mirror structure of the way it's put together. So it has this hexagonal structure like a beehive. And that's the most efficient way to do it. The bees figured that out before we did, but that's the best way to do a structure. Okay, so this is cosmology. I'll give you my email. It's also in the directory and stuff, so you have to write it down now. But so if you have any questions after the class or between classes, just text me or email me or call me if you want. Okay. So this is the course. Just go over it a little bit. Today, we're going to do galaxies in the universe. Today, I'm just going to tell you what's in the universe. All right. So we have some basis of what we're trying to understand. And if the word cosmology is new to you, it is the whole bit, everything in the universe. It's the biggest thing in science we can possibly do, the whole universe. But except that maybe there might be more than one universe. So So that's what we're going to do today. Tomorrow we're going to do, next week rather, we're going to do expansion of the universe, which is the universal expansion. That's not new news. That was first published in 1929, but it's the one thing I get the most questions about from the public. So I'm going to spend some time talking about that expansion. And it also forms the basis of our understanding of the universe today. The cosmic background, microwave background is a crucial change. That was published around 1965, and it changed cosmology completely. Before 1965, cosmology was known as a field with lots of theories and no data. Now we have lots of data, and the whole field has changed. On the 25th, we'll talk about origins of the elements. That's a class that I've added. In the last time I taught this course, I alluded to the elements a couple of times, and there was a lot of interest about that, a lot of questions about it. So I've written an extra lecture to talk about the origins of the elements, and that's why this course is a little bit longer than the typical one. We typically were 3 to 5 lectures, but now I'm doing 6. Love it. Dark matter and dark energy are 2 of the big unknowns, mysteries in astronomy, things we don't understand yet. And one of the neat things about astronomy, I think, in a class like this in particular, is that in astronomy, it's easier to get up to the very most important questions and the deepest questions and the biggest unknowns relatively easily, much more easily than in physics or chemistry or mathematics, certainly mathematics, where you know, it's hard to know what the people today are working on. But maybe we're just not that far along, and we still have a lot of questions in astronomy that are easy to understand. Then the last lecture will be the first stars and galaxies in the universe. That is what really James Webb is doing for us. That is what James Webb was designed to do, and that is what it is working on. So that's the overview of the course. Okay, and I'm going to try an experiment in this class because I have, you know, a very varied audience. Some people have never taken a science course, which is fine, and directing it to you too. But some people have a PhD in physics or something. And so to keep everybody interested, I'm occasionally going to talk about something that's a little further than a course like this would be, just for those guys who think they know everything. Well, for the people who have a background and to keep them interested. And if you don't follow it, it doesn't matter, okay? If you can either try to follow it, and if you don't follow it, pretty soon I'll get to something that you do understand, or if you just want to zone out when you see this sign, this cat, or you can check your email or something, or whatever. Okay, so that we'll try that. I don't think I'll do that today, but in the coming lectures. All right, so today I want to talk about how big things are and how old they are. Pretty direct. You might have heard of the term light year. Let's just talk about that a minute. A light year is not a time measurement, it's a distance measurement. And it is the same kind of thinking as when we say it takes 45 minutes to get to San Jose. And that is a distance measurement, not a time measurement, because you know that when you drive, it takes about 45 minutes to get to San Jose. So that's a different way of saying distance rather than that it's whatever it is, 55 miles or something, okay? And that is a convenient measurement for us in astronomy because it is the distance that light travels in a year. That's a light year. So it's the distance that light travels in a year. Now that's not intuitive, but it can become that way. One thing you know is the moon, which is pretty far away, but it takes 1 second for light to get from the Earth to the moon. You might have noticed that during the Apollo 11 missions when they were talking back and forth, and it was broadcast on the TV. They would say something, and then there'd be a pause, and then there'd be an answer, and that was for the light for the sound, which travels at the radio waves rather, which travels at the speed of light to get to the moon and back. And you know, sometimes they were thinking about what they were going to say, but all right. Now, the sun is a lot further away. It takes 8.3 minutes for the light from the sun to get to us. So you're seeing the sun not as it is today, but as it was 8.3 minutes ago. So if it stopped shining this minute, this instant, we wouldn't know about it for 8.3 minutes. Okay. So in that sense, we can look back in time in astronomy, and we'll be using that throughout the whole course. All right, well, that's the, I'll give you some nearby things. So that's the moon. It's a light second. I love this picture because this is an aside, because we see a man in the moon, but the Native Americans throughout the Americas apparently saw a rabbit in the moon. Okay, if you see I see a rabbit, you know, there's its head, there's its ears, there's its paws, and hind feet. Its tail. Oh, yeah. So it's a bunny rabbit. You're really lucky to come to this course. All right, the sun is 8.3 minutes away. It's 93 million miles. So you can already see that it's kind of a little bit easier to talk about this light travel time than miles. I mean, I think 93 million miles is barely something we can comprehend, and we're just starting. Okay, now here is a nice picture of Neptune, which the James Webb took. See, 6 rays, and shows Neptune and its rings, and its light travel time is 4 hours and 8 minutes. So it's pretty far away. And that's just in our solar system. All right, now, but stars, which I'm distinguishing from planets. I mean, they both look like stars in the sky, but planets are the things that move in the sky, and stars are things that are stationary. The nearest star to us, which is called Proxima Centauri, is 4.4 light years away. So the light left 4.4 years ago. So that's a long time, and it's a great distance. I think you can kind of get the idea that space travel is pretty tricky, despite what you see in Star Wars and stuff. It was a lot of work for us to get to the moon, 1 light second away, and we haven't done it with humans in it. So human space flight is still something way in the future. Okay, here's Orion. It's a constellation most people can recognize. Here's the belt of Orion. Here's his shoulders. Here's his sword. Here's his feet. So this is Orion constellation. It's maybe the most dramatic constellation. And this is Betelgeuse, which is 642 light years away.
How do you pronounce that? Betelgeuse?
Betelgeuse. It's an Arabic word. Arabics have been doing astronomy for a long time.
What's the word in Arabic, sir?
I don't know what it means in translation. That's a good point. Yeah. Does anybody know? Okay. Well, that's something to look up. Notice also that it's orange, whereas everything else is pretty much blue. Betelgeuse is a red giant star, hugely bigger than our sun. If Betelgeuse were where the sun is, we would be in Betelgeuse. It extends out to here. And so it's a late stage of stellar evolution. We won't be talking too much about that, but it's interesting anyway. This here in the sort of Orion, this sort of fuzzy patch, is the Orion Nebula, and that's one of the nearby regions where stars are forming today in our galaxy.
I have a translation.
Oh, okay. Somebody else.
It's in Arabic, it means the giant's shoulder.
The giant shoulder. Okay, that's good.
All right. Makes sense.
Good. Okay, now here's Andromeda Galaxy. And this is our first galaxy. Galaxies are huge accumulations of stars held together by gravity. And this is almost the nearest galaxy. The Magellanic Clouds are much closer, but it's the nearest large galaxy to us. And this contains about 300 billion stars altogether. Our galaxy, the Milky Way, the one we live in, is also a galaxy of this type, slightly smaller, about 200 billion stars in our galaxy. Okay, so that light from that left 2.5 million years ago. So it's 2.5 million light years away. So that begins to be something that's hard to comprehend. 2.5 million years ago, we weren't like we are now. That was the Homo habilis creatures, the first tool makers, or at least early tool makers, were on Earth now. This is a picture of Oldaway Gorge, where the first Homo habilis was found at this site where this monument is. And this is the type of tools that they were making. So just to give an idea of the size. But that's not, and so again, in terms of dates, the Earth is about 4.65 billion years old. And here's another galaxy, a rather dramatic one. It's 20 million light years away. So light has been traveling for 20 million years to get to us. And here's another one. This one's 29 million years. Just to show you, this is a Hubble picture, and this is a JWST, which stands for James Webb Space Telescope. I'm gonna say JWST at times. Telescope, and they show us different things, because the Hubble is looking at visible light. The James Webb looks at infrared light. So we see different aspects of things. But you can see here a typical spiral galaxy. This one is seen edge on, and we see them in random orientations. Showed the previous one was face on. This one is more or less edge on. This is clouds of dust and material in the galaxy, and we're looking through the edge. You see here this halo, it's light, diffuse light. There are stars up here, but most of them are on this very flat disk. And galaxies come in groups and clusters. That's in the bigger thing than a galaxy is a group of galaxies. This is the famous Stephan's quintet. In fact, though, only four of these, there's two galaxies here, four of these 5 galaxies are at about 290 million light years. This one is actually a foreground galaxy, a close galaxy. So it's not as far away, but but when we look out, we see everything on top of everything else. So when you see galaxies in the distance, but then you see a star field around it, those are stars in our galaxy. And we have to look through our galaxy to get to the distant points. So that's the question right away, which we'll address, but let me just bring it up here. How can you tell how far away things are? That's really critical for us to understand it. Okay, now it's all fun to see record holders. Right now, this object is the thing that is the furthest away that we know so far. And it's the light has traveled 13.38 billion years. Now that I will qualify that slightly. That's the number that's given, but that depends a little bit on how what we call the model of the universe. That depends a little bit on how the universe has been expanding and so on. So it's somewhat model dependent. But that's the light travel time, 13.38 billion years. And what is this thing? Well, it is a galaxy, but it's kind of different from the nearby galaxies. So this is one of the first things to form early in the universe. This is what JWST is looking at. That's what we sent it up there to find. That's really cool. So we'll talk a lot more about those things. Okay, so we look back in time. I just want to emphasize that we're really have an advantage in astronomy. As right, a paleontologist sees a bunch of fossils and looks back in time, but doesn't really see the live things. And so we see galaxies as they were long ago. We see galaxies like ours, and we see what galaxies like ours were like long ago. What our galaxy was like. See, okay, I'll take a question too.
Why are the galaxies like discs like that? Why aren't they balls around the center?
Okay, yeah, did everybody hear the question? Why are galaxies disks? Why aren't they balls? A galaxy is held together by gravity. And when a galaxy forms out of dust and gases that are condensed by the gravity, but we find that the initial thing is they're also rotating. That big cloud is rotating. So, like when you're on a merry-go-round, you tend to be pushed out to the sides, but nothing vertically. So the galaxy can compress rather, with gravity in its vertical direction, that is the spin axis direction, but it has a harder time contracting along the other direction. And that's why we see flat things. That's why the solar system is flat, for example, why we have the ecliptic. When you look out at night, the stars are, the planets, when you look in our solar system, the planets are more or less, not exactly, but more or less in the line that the sun traveled earlier in the day. And that's because our solar system formed out of an ancient rotating interstellar cloud. It's a much smaller system than a galaxy, but it's the same idea. And it then compressed along the rotational axis. So when you see the planets in a line, or when you see where the planets are, you're seeing that ancient disk of 4.6 billion years ago, out of which our solar system formed. Okay. All right, one or two more questions and I'll go on.
So. Why then is it always rotating? Is the whole mass rotating so that?
Yes, it keeps rotating.
Initially, even in the beginning.
Initially, we don't know. Okay, that is conditions that we're investigating. But it'll keep rotating until something stops it. You have to put a torque on it. And you know, there's not a big strong torque on the Earth, and it keeps going around the sun. And it will be. I mean, bad things are going to happen to us, but that won't. It'll be over.
But the galaxies start as a ball and then change shape over time, so a young galaxy will be more round and a older galaxy will be more elliptical and flat.
Somewhat, something like that. And that was our picture of galaxy formation, or at least it's a simple mathematical picture that you can deal with. But what we are finding is that these very early galaxies, like the JDIS system that I showed, are irregular shaped. They're not, and the whole business of the spiral arms, the flatness, that grows in time.
So there are still elliptical galaxies.
Yes, they're.
And I think what the difference is they don't have clouds of gas and dust to slow things down when they pass back and forth through the plane.
Yeah, that's correct. The elliptical galaxies. Okay, I'm sorry. There are other kinds of galaxies, and I think the next slide may actually show one. Or no, let me see if I can find one. There, this one. This is an elliptical galaxy. A lot of our galaxies don't have the spiral arm shape. They're just a diffuse big thing, and that's actually I think more common than spirals. But spirals are more photogenic, so you always see that. But elliptical galaxies have a long history, and what happens in galaxy evolution is that galaxies collide a lot. I showed that small grouping and the clusters, they collide, and when they collide, they disrupt all of that structure, and it eventually settles down more or less into an elliptical galaxy. Okay, let me go on a little bit here, and we'll take some more questions later. Let me go back to where I was. Okay, so I want to talk again about the galaxies and the history of it. The first time we saw galaxies, even recognized that there were spiral arms in them, was Lord Rosse in 1845. And he was an amateur astronomer, but a real rich lord, and he built the biggest telescope in the world for himself and started looking at stuff. And he discovered spiral arms. No cameras then, so he sketched it. And this is the galaxy M51. And this, I think, is one of the earliest photographs of a galaxy. M51, same galaxy. And you see it has spiral arm structure, but it also has this little galaxy which is interacting with it. So there's a galaxy collision going on here. And here is M51 with the Hubble photograph, so you can kind of see what's going on. It is a very well-defined classical two-armed spiral, but then there is this thing coming in at it, and it's apparently drawn out some material here by gravity. This is actually a galaxy you can see with small Emeritus telescopes that.
Which constellation, sir?
That is way up north in I think in the Canis Majoris in there, okay, near the Big Dipper. So I think more. Well, the Big Dipper circles. It's further north than that. Way back, and here is a picture of the James Webb Telescope took. I think the Hubble pictures tend to be prettier, but we see a lot more detail in the James Webb.
Roger,
Mm-hmm.
the colors that we see on these photographs, are they a product of manipulation of the pixels?
Yes.
To bring out the different.
They're all products of manipulation of pixels. The visible ones are set up, they take pictures in different filters that have certain wavelength transmissions. And they put it together, trying to mimic what the naked eye might see. But that's a judgment thing. The infrared is completely, we can't see that at all. So those pictures are just to guide our eye, those colors, because we can't see infrared. Okay, this is just like looking at these galaxies. This is one that's often called a galaxy very much like ours. If these guys are looking at us, they're seeing something very much like this. Again, you see all the nearby stars in our galaxy. See, 200 billion stars. That's a lot of stars. I mean, we're so used to billions now because Elon Musk has billions of dollars and stuff. But if he sat down to count $1 billion and counted $1 every second, it would take him 32 years to get to a billion. So billion is still a big number. All right. This is an elliptical galaxy, M87. This is actually a giant galaxy. It's 10 times as massive as our galaxy, and we're one of the massive galaxies. Okay, so this is a giant galaxy. Notice this jet it has coming out of it, which is thousands of light years long. It's a huge thing. And we'll get back to that. These are very significant events here. One of the, well, let's see, I think, yeah. One of the things is that the next shot is the very center of this galaxy. And we now know there's a giant black hole in the center of that galaxy. So I'm just jumping ahead a little bit, things we'll be talking about. So here's what the black hole, now we can't see a black hole because it's black, but we see its shadow. That's this here. And this is a humongous black hole. It's as though 6.5 billion suns all collapse into a black hole. Or they have this reputation of eating everything around them. And things fall into black holes and the black hole grows. So to give you some idea, if our sun became a black hole, now we don't know any way that it could, but if it did, its size would be about 6 kilometers in diameter, about the size of Santa Cruz. But if the Earth were to become a black hole, it would be about 2 centimeters in big size. Okay, but look at this one. This is bigger than our solar system, with these 6.5 billion suns. It's a gigantic black hole. What you see here is that under the huge gravity of such a thing, gases circle at the speed of light, almost the speed of light, and that radiates, and that's what we see.
Why does it say Pluto in the center?
This is the size of the solar system, the distance from the sun to Pluto.
Oh.
And Voyager, which has left the solar system, would still have barely left that black hole. So, I think so you don't want to get near one of these things.
You'll get a bad sunburn real fast.
Really amazing thing. This is an amazing result, by the way. In order to get this picture, they had to tie together telescopes from all over the Earth. So we had so they had a huge, effectively a big telescope, almost the size of the Earth. Not in terms of light gathering power, but in terms of resolving power, resolution.
Radio telescopes.
Yes, yeah. Okay. Well, here's an artist's idea of what it looks like. There's a black hole in the middle, and then there's all these swirling clouds of relative and extremely hot gases around. And then oftentimes we see that along the rotational axis, perpendicular to the flat disk again, there's a jet. That's the jet that we're seeing from M87.
Why is it getting
We don't have a good picture of that, but as material flows in, see, some of this material in the disk is going to flow into the black hole, but some of it misses a bit, and then the black hole shoots it out. It gets shot out along the axis where there's less gravity. Okay, well, galaxies interact. Here's a nice case here. Two smashing into each other. two spirals. This is the JWST picture. This is our picture. So and this happens pretty frequently, and it's very important in the evolution of galaxies. It's going to happen to us too. About 4 billion years from now, Andromeda is crashing into our galaxy. And
The space, Roger, isn't the space between stars and things in our galaxy such that when two galaxies combine, it's not like there's collisions of stars and.
that's right. The stars are so far apart, they still don't collide even when the galaxies collide. But what does collide are the gas clouds. They smash into each other, and we see that effect. They get hot, they compress, they form new stars at times.
Don't the gravity fields collide also?
Yes, the gravity, it moves the stars around, but they don't physically crash into each other.
But the gravity fields merge then together and become a single gravity field.
Yes, yeah. As the mass becomes single. And the predictions for the collision between the Milky Way, that's us, and Andromeda are that we would form an elliptical galaxy. The combined system would form an elliptical galaxy. But that would take a while. That's another 2 billion years or so that it would take.
If this is 6 million light years away, how do we know that it even exists?
Well,
Especially since they're colliding all the time.
well, they're changing as of this minute, but we look back at the universe 13 billion years ago and we see stuff. It's there. It's kind of hard to believe that everything disappeared.
So it's in real
It's-
time, or it's not in real time? When you're taking a picture, it's still in the past.
We see into the past. You're seeing me as a fraction of a second, a tiny fraction of a second, about a nanosecond or something, as I was. Okay. And you could argue maybe I don't exist anymore. I'm trying to answer your question. Okay. Yeah. It certainly, if you're willing to say that there is this time in the whole universe that's now, that's a question that's a little dicey. But if you say there is a now in the whole universe, then what we're seeing on those distant galaxies, that is not what they look like now.
Right.
Okay. All right. Here is a cluster of galaxies. This is the Virgo cluster. And there's hundreds of galaxies all grouped. This, by the way, is M87, that giant elliptical that I just talked about. This is another elliptical. And you see lots of spirals and others. And one hint is that in these large clusters, you often see a giant elliptical in the center, which is a strong hint that, in fact, what's happened is lots of galaxies have collided and it's fallen to the center, this gravity field. So galaxies form in clusters.
Roger?
Yeah.
Over here.
Yeah. Okay. Well,
So, what in the world is in that black hole? Because you mentioned that there's tons of suns that go in there.
yeah,
And I mean, not even the light is getting out.
that's right. Nothing's getting out.
So what is?
Well, we can't. It's outside of our ken. We can't see it. There's the black hole has the property of mass. It does have mass. Okay, measure the mass. When you have a black hole that's 6 kilometers in size, that'll be a solar mass of the sun. If you see, if now we don't know that we can make small black holes like that, but that's what it is. But the matter is gone, and we don't know what the state of the matter inside the black hole is. By the way, the size is strictly proportional to the mass. The size of a black hole is strictly proportional to the mass that's gone into it. So you could calculate how big a black hole you would make.
Even if we're vegan?
All right. Now, this is a neat graph, and but it takes a slight bit of this description. The Sloan Digital Sky Survey was to survey the whole sky and see how galaxies are distributed in the sky, how they are set up. Now, what you're seeing here is a pie. Take, you know, the universe is three-dimensional, so we'd see everything. But let's take a thin slice through that sphere of the universe, and we look out And there's no galaxies are plotted here because these two directions, we look through the plane of our galaxy, of our own galaxy, and that obscures the distant galaxies, so we can't see much there. But when we look perpendicular to the plane of our galaxies, then we can see galaxies, and that's what you're doing here. So it's a thin slice looking out, and the distance here this is 1 billion light years, this is 2 billion light years. And now look at the distribution. Every blue dot here is a galaxy. And focus first out here, things get dicey because they're so far away, they're hard for us to see. But here we are seeing the galaxies. And look at this. This is not a random pattern. This isn't what you would see if you spilled all the peas on the floor in the kitchen, right? What you're seeing is there are these big structures of galaxies, big filaments where they all line up in order. And then you see empty spaces, we call voids, where there aren't many galaxies. So this is the structure of the universe. And it's not just a random structure. So it is telling us something about the universe. And that's what I want to emphasize, that we can learn about the universe, and we'll go into that. I won't discuss it in detail now, but by the structure of the galaxies. That is telling us something about how the universe has evolved. The other thing to look at is that wherever you are, here or here or here or here, you see on a large scale the same thing. The universe is homogeneous, it's the same everywhere you are, and isotropic, same in every direction. If you look on a large scale, obviously it's not isotropic in this room, right? Look in that direction, it's different from that direction. But on a large scale, like 300 million light years or so, the universe is uniform and isotropic. The galaxies are spread that way.
It almost looks like
Okay.
blood vessels in your eyeball. That's what it reminds me of.
Yeah, blood vessels in your eyeball,
Like the-
yeah, also like a bubble raft or a foam raft, a little bit like that. Huh?
Okay.
Can I ask a quick question? Oh, I'm sorry.
Okay, yeah, go ahead.
Is it assumed if we could see through our axis, it would look the exact same, I mean, similar?
If we could,
If we could look where we can't look?
yes, absolutely, yeah. That is the assumption that we've made for
Okay.
centuries now, right? Ever since pretty much Galileo or so. Before then, we thought we were in a special place in the center, but now we no longer believe that.
Could it be gravity is what's determining that pattern?
Yeah, it is gravity, but in a tricky, very tricky way. Okay.
Yeah, I can.
Yeah, you mentioned, I think, in previous that 95% is dark energy estimated. Are these white spots or dark matter? Sorry, dark matter. Are these white spots dark matter?
No, the dark matter is actually associated with the galaxies, with the blue things. That is also affected by gravity. So dark matter it's about 23% or so of the mass of the universe. There's also the dark energy. But the dark matter is actually associated with galaxies. We think, and there's lots of evidence to show that there's a huge halo of dark matter, something like, I'm trying to remember, at least 10 times of the visible matter in our galaxy. All right, now, having said that, I will raise something else interesting. This is a similar type of plot, but of something else. This is of the quasars. Probably heard of the quasars. They are the extremely bright things in the universe. And in fact, they're so bright, we can see them almost all the way back to the beginning, 14 billion light years. So this is the distribution of quasars, and the distribution is actually the same as the galaxies, and quasars, in fact, are in the centers of galaxies. But this we can see much further back. And you see now there's a difference here. There aren't many quasars near us. And there aren't many quasars way out here. They become rarer. So, and those are both real effects. And so the universe, while it's homogeneous and isotropic, in time it changes. Okay, in the early universe, there weren't many quasars. Then quasars became abundant, and now we don't see many here. Okay, so this is a quasar about here, and here I've overlaid the previous galaxy picture. See, that's just 2 billion light years. That's just how far. So quasars will get a much larger part of the universe.
So are we near the center?
Yes, we're looking here.
But are we in the center?
No, it's everybody in the universe thinks they're at the center because they look out and sees things.
And you're saying we're in the middle, so are we in the middle?
Perspective.
Just from where we were looking, okay? If somebody out here was doing the same thing, they would have the same diagram. Right? Yeah, okay. See, it's if you're in the forest, in a big forest, everywhere you stand, you see forest trees all around you, but that doesn't mean you're in the center of the forest.
Well, I think it's fine.
All right, yeah.
I'm just sort of trying to, but it looks like you're showing this pattern of denser in the middle and less dense on the
Yeah.
edge, so does that, if we're not in the middle, it's not, I don't understand that.
Well, everybody, the person, let me go back to this one. The person standing here is going to see a big circle surrounding that himself. And when that person looks back 14 billion years, they'll see fewer quasars there too. Okay? Yeah?
What's a quasar?
Okay, a quasar, quasi-stellar system is, we now know that these were discovered in the 1960s and were a mystery for a long time. These very bright things, very, very far away. We now know that quasars are in the center of galaxies and that they are giant black holes. And that the reason that we're seeing this extreme light is basically the material surrounding that black hole, which becomes extraordinarily luminous. And these gases are moving near the speed of light. And there's huge amounts of it. And they become another term is active galactic nuclei. And we can see those. So the quasars are a phase of galactic evolution.
Every quasar is a galaxy.
Yes?
So to get back to the first point. So wherever you stand, you will not have quasars near you,
That's right.
but that feels like.
But a long time ago, you were seeing galaxy quasars near you, right? When we look about 12 billion light years away, 12 billion years back, that's what the universe looked like, and that's what our surroundings looked like 12 billion years ago. So we would have seen more quasars 12 billion years ago. We're not seeing them now.
Do they collide?
Galaxies collide. Yes. Yeah, absolutely. And the quasars in them collide. But that's an event we're looking for but haven't seen. If you have just imagine two of those really giant elliptical galaxies with a really, really big black holes. And now the two elliptical galaxies collide. Oh, the black holes collide. We have only seen black holes of the size of in the order of 20 to 40 solar masses collide. Okay, but it'd be interesting to see one of these really big events. People are looking for that, and it must have happened, but we haven't seen anything like that yet. That is not. That's also a technical problem. The detectors that we have to detect gravitational waves from black holes are not sensitive to the collision of these giant black holes. Those are very slow events, and we can't measure those long wavelengths from slow events. Well, that's good. That's probably more than you wanted to hear. It's interesting. All right. So this is what I want to talk about on large scales. And if you ask me what the scale is, it should be about 300 million light years. Okay, let's take a break for a few minutes. Well, did you pass by? All right. I want to get down to business a little bit here and talk about how we actually know how far things are. That has been a crucial thing in the development of astronomy. In fact, you can almost do the history of astronomy by how we learn how to measure distances to things. Obviously, when you look out at the stars, you don't know whether they're near or far. A star could be bright because it's intrinsically very bright and far away, or it could be bright because it's not very bright, but it's real close to us, right? So just looking at the stars, you can't say the bright ones are closest to us and the faint ones are furthest away. That's actually not true. So it's more complicated than that. And the way we made progress was through the Cepheid variables. And this was done, it has a very nice story. It was initiated by an astronomer, Henrietta Leavitt, in 1908 with the Cepheid variable stars. And here's the deal. Okay, as I said, when you're looking out at Orion, you can't tell which of these stars are nearby and which are far away. No direct way. So how do we measure things? Well, here's a kind of a hint. This is a lighthouse. It's far away. Now, you know from say the structure of the lighthouse roughly how far away it is. So there's a hint. Well, there's lots of other things in the picture. So it's but there's a hint from looking at the lighthouse how far away what it is. Okay, you say I recognize a lighthouse, and now you know that lighthouses have lights which are sort of similar to each other. They have a certain brightness, right? They're not all the same, but give me that. And so now you look at how bright the light is, and now you in your mind say how far away this thing is, because you know how light gets fainter as you go further away. So the crucial thing was to recognize what this thing is. See, if it were just some arbitrary flash of light, you again wouldn't know. But if you recognize what it is, then from the brightness of the light, you can tell how far away it is. I mean, a more common example might be distant car lights, right? You see two lights and figure, well, that's a car. And if they're very faint, you know the car is far away. If they're bright, you know it's nearby. And again, there's other hints too, but you gotta go with this one. All right. So there are certain stars called Cepheid variables, which vary in brightness in the space of a few days. And they're called Cepheids because they're in the first one was found in the constellation of Cepheus. And here's one that you can see, and here's the star. I'm told to use the. Oh, this is hard to do. And you can see it in the space of a few days, this star gets brighter, and then it gets fainter, and then brighter again. The reason for the squares is that this is a distant one in a distant galaxy, and we're at the resolution limit of the telescope, so we're seeing the pixels shapes. But you see, it varies. And Henrietta Leavitt studied this effect, and what she did, it was a clever thing. She decided, I'm going to look at all the Cepheids in the Magellanic Clouds. Magellanic Cloud is a galaxy very close to us. And those Cepheids, I don't know how far away they are, but they're all more or less at the same distance because they're all in the same cloud. And then she noticed that the brighter Cepheids varied more slowly than the fainter ones. And the fainter ones varied rapidly. And that was the key. Because then she said, if that is true for all the Cepheids in the universe, then by measuring how rapidly it fluctuates, I can get at its luminosity, at its intrinsic brightness. And then from the intrinsic brightness, you can get the distance. Once you calibrate that, you have to get the distance to the Magellanic Clouds in some other way. Okay, so that was the way it worked. The Cepheid stars vary rapidly, low luminosity, high luminosity Cepheid, it's very more slowly. And so that's a picture of how that works. Okay, here's a fainter one and it varies pretty fast. Here's a slower one and it varies slowly. Now you calibrate this. Here's the period. So these are the ones that vary slowly. And here is the brightness going up. This is the astronomer's magnitude stuff, which I'm not going to explain. Okay, just brighter up higher. Okay, and so you can see there's a very good correlation here of the Cepheids with their brightness. And so from just looking at the period of a Cepheid, you can tell what its intrinsic luminosity is, and then you compare it to the brightness that you see, and then you know how far away it is. So you can tell the distance to Cepheids.
But there's no trick.
But
There's no trick to know that it even still exists.
do any of us still exist? Right. These are just a couple of fun photographs. This is Henrietta Leavitt at Harvard, and this is Annie Jump Cannon, who also became a very famous astronomer. This was an interesting thing. This is Pickering, and Pickering was looking at a lot of statistical things in astronomy. In the early 1900s, there were still lots of questions of where the stars are, how they're distributed, everything like that. And there was lots of difficult work to do, but no computers except these women. And he called them his computers. And Pickering had this theory, which I think he had some experimental evidence for, that men weren't very good at this tedious work. And I think he had some guys who did pretty badly. And so he hired women to do that work. And they did the work. And some of them, particularly Anne Cannon, became very famous astronomers. And I don't think Leavitt is in this picture, but she's in this picture. So that was Pickering's computers. And now here's another Cepheid. I just want to show, this is a little beside the point, but I just want to show an issue here about why the Webb is so good. Here's the Cepheid. Again, we're looking at the limits of what these telescopes can do. So we're looking at pixels. And here's the Cepheid. But here's a nearby star, and see the light splashes over into the Cepheid. So that damages our ability to get it at its luminosity. Whereas with the Webb, which has a much higher spatial resolution, that star does not overlap the Cepheids. So that's another way that Webb is really helping us.
So Roger,
Yeah.
so you said something about Cepheus being in one of the Magellanic clouds.
Yeah.
And that's southern hemisphere, so how did Leavitt see them?
From this, we had telescopes in the southern hemisphere at the time. Yeah, she analyzed the data. I don't think she got the data herself. I'm not sure about that. Okay. Okay, the next step is Edwin Hubble, who you've all heard about, Hubble Space Telescope. He was certainly the most important astronomer in the early part of the 20th century by far. So this is Hubble, and Hubble worked at the 100-inch telescope, which is on Mount Wilson outside of Los Angeles. And this is the telescope which was pictures taken somewhere around 1910 or 1915. It was the largest telescope in the world. And when we say it's 100 inches, we mean the diameter of the collecting area. Okay, so it's the mirror, which focuses the light, like a lens focuses light, is 100 inches in diameter. So about 2.5 meters. And that's what, and when I give telescopes by their size, that's what I mean. It's the diameter of the mirror. Wow.
Message from outer space.
Are we online, or is everything working? Okay. All right, now,
Someone's phone is ringing.
okay, we have,
Yep.
I'm gonna get back to this.
Scan.
Here's a picture of the Mount Wilson Observatory outside Los Angeles. It was the largest telescope on Earth at the time. And what Hubble and his co-worker Humason wanted to do is they looked at these galaxies, and at that time, before 1925, we saw these spiral arms, these galaxies, these fuzzy things, and nobody knew what they were. Are they nearby things? Are they stars forming? Are they far away? What is the deal with those things? And there were big arguments and big debates about, some people said they were near, some people said they were far. There's a famous a debate between an astronomer from Lick, from us, and another one from Harvard. And the Harlow-Shapley debates about whether the galaxies were near or far, but it wasn't settled. And it wasn't settled because of an interesting reason that the astronomer from Lick had the right answer, that they're actually far away. I'll give it away. But he had the wrong reasons. And the astronomer from Harvard had the right reasons, but came to the wrong conclusion. So they wanted to find out what these were. And so Hubble looked at the nearest galaxy. That was the technology at the time. Here I'm showing a recent picture, not Hubble's. And the key was he could locate Cepheids in the galaxy, in Andromeda. And this is a recent picture. So here's a variable Cepheid. You can't see it here, but with higher magnification, you can see it's changing brightness. And this is Hubble's original picture. This is a negative of the Andromeda galaxy. So the bright turns out dark here. And he looked here for stars, and here he saw a variable, a Cepheid variable. Because at that instant, he knew he had the answer. How far away is Andromeda? And here's some more. His V's look like N's, but so there's another variable here. And 6 October 1923, and there's a variable. So he measured the variable stars in Andromeda, Cepheid variables, used the calibration that Leavitt had first made about how, when you measure their variation, what's their intrinsic brightness, and then he compared to the brightness he observed, and he had the distance to Andromeda. And for that, he got 2.5 million light years. So that answered the question. The galaxies are far, far away, much further than the nearby stars that we see. And that set up what was at that time called the island universe idea, that the universe is composed of galaxies with millions of stars, billions of stars, empty spaces, pretty much, and then another galaxy, galaxies all over the place. So that settled the thing that we now know that galaxies are star systems held together by gravity, and that they are distributed throughout the universe at huge distances.
How did they measure luminosity?
How
did they measure luminosity?
you just you compare it to the brightness, say, of the moon, or the brightness of nearby stars, and then you compare in your photographic plate how bright that image is to the nearby things.
Instrument to do that with?
Yes, a photographic plate will do it. They also have photometers. Before that, they did it by eye. They estimated, but it's always comparison to other stars. So 2.5 million light years to Andromeda, and that's just a really nearby galaxy. Why is this doing this to me now?
Popped out of screen share. No.
Sure, this is doing things right. And so I'll do a few more. This is one at 45 million light years away. Here's some at 60 million light years ago, another nice group. By the way, this is a JWST picture. And so you see, these are the distant galaxies. These are nearby stars that we're looking past that are in our galaxy. Here is the Coma cluster, 323 million light years away. This is one of those clusters, but remember when I showed the galaxy distributions, there were these long filaments of galaxies. this is one of those things. And here's a neat group that, these are all going to collide, and people think it's going to form a big elliptical at some time in the future. Yeah, it's really neat.
Red looks like that.
Yeah.
What is that?
These are reddish galaxies. This here,
Yeah.
this is a spiral seen edge on, and these are the dark clouds that we see even in our own galaxy, that form in the spiral arms. And it's out of those that stars form. We formed out of clouds like that 4.5 billion years ago.
Roger, how far apart are the individual galaxies in that cluster? Can you tell
Well,
us?
you could kind of estimate a galaxy like this is about 100,000 light years in diameter. And so you can see these are of that order now, so they're pretty close together.
100,000 light years.
Well,
Well, relative.
all relative, point of phrase. Just to give you an idea of the structure now, we can't get a picture of our own galaxy because we're in it. But we look a lot like Andromeda. We're the same type of spiral galaxy. And if this is the center of our galaxy, then we would be about 30,000 light years from the center, out here in the suburbs, in a spiral arm.
Now, is that Andromeda on its way to us in the lower right-hand corner?
This is Andromeda.
Oh.
This isn't our galaxy. This is Andromeda, and I'm using it as an example of ours. This is a little diffuse galaxy, elliptical galaxy that's gravitationally attached to Andromeda. And there's another one. We have two galaxies like that too, the large and small Magellanic Cloud. They're little galaxies that are orbiting us. So that's a structure. So anyway, here's the light years. If you want the distance in miles, here it is. See, that's kind of hard to deal with. And this is a lot better, right?
14 quintillion miles.
Okay. Now it's I just add, you can forget about this, but astronomers actually use parsecs and not light years, but they're less intuitive. Parsecs are less intuitive, so I'm going to stick with light years in this course. But if you read some of the astronomy stuff, you'll see parsecs. And just remember, a parsec's about 3 light years. All right, here's our own galaxy. And now you can kind of see with the Milky Way. When we're looking in here, this is the disk of our galaxy. That's the Milky Way. When we're looking up here, we're looking perpendicular to the disk. And here, we're looking along into the disk. And you can see those dark things, these are interstellar clouds, which big masses of gas, and there's also what we call dust, large, somewhat analogous to Earth dust, a little smaller. The X here is what, if you're looking in that direction, and this is Sagittarius, you're looking at the center of our galaxy, but it's not obvious. The center of our galaxy is completely obscured by this dust stuff.
Where's the black hole?
Pardon?
The black hole.
The black hole's right in the center.
Right in the center.
Yeah.
Are there still stars being formed on the outer?
Yes, yes. Like in Orion, we're seeing stars forming now. And there are a lot of star forming regions. They're all over the galaxy, actually. There's some star formation going on near the center of our galaxy. And it tends to be, it does tend to be in spiral arms because the clouds there collide with each other. And that sets up big shock waves, and that can trigger a collapse through gravity. Okay. Okay, well, just to give you an idea of the size, our galaxy rotates. This big spiral rotates once in 230 million years. Last time we were here was 230 million years. And 230 million years ago, the continents were all together still. And then the first dinosaurs appeared few million years around that time, primitive dinosaurs. And the flowering plants evolved when we were sort of a third of the way around. And then the dinosaurs continued to evolve, and about 100 million years ago, the continents began to look like what they're looking like now. And then the dinosaurs, the famous dinosaurs, Tyrannosaurus, were here. And then about 60 million years ago, big bolide, big asteroid hit the Earth and wiped out all of the dinosaurs and caused mass extinctions all over the world. That was a quarter of the rotation through. And that set up the opportunity for the mammals to come in and evolve, and our ancestors come in. And all of human history, which is about 6 million to 7 million years, people typically, the hominid history, you know, when the hominid branch separated from the chimpanzees, that was about 6 million years, which is just this small region here. And then here we are today. Okay.
At the center.
So this is the, this is not the center. I'm just trying to clock hands, okay? Are you? All right. Okay, so that gives you an idea of the galaxy, and I just want to tell you, I mean, things are really big out there. I'm not sure I should say this, but there was a test answer, or it was asked to estimate the size of the universe on the test, and he wrote, well, it's F blank big. It's actually the right answer. No. Okay, so this is why I was emphasizing galaxies. They're the signposts. They're the things that we see at the greatest distances. And when we want to study the universe as a whole, at its biggest dimensions, and its most ancient times, it's the galaxies that we look at. Those are the things that we see in the furthest distances. Okay, and I think I got a little out of order here, but so again, repeating, I think I've said all this. Diameter is about 100,000 light years. Okay, and so you can kind of see here, this is the edge, and that's the edge we're looking through when we see our galaxy. And here is what our galaxy would look like more or less face on. Okay, and then back to here, which I started with. This is the most distant object that we can see. It is a galaxy. It's a small galaxy. It's irregularly shaped, but it's very, very luminous. And these are the things that you might have been reading about in the newspapers that James Webb is discovering, because we're finding galaxies. This is very small compared to our galaxy. That's how they start. And but we're finding things, galaxies with lots of stars in them, very bright, very, very early in the universe. And that's the mystery right now. Where this thing, the universe was only about 200 million years old. Only 200 million years. Remember, now it's 13.8 billion years old. And we thought it would take longer to form stars and galaxies than 200 million years. But when the universe is only 200 million years old, 250 to 300, you know, we're still arguing about that a little bit. But then we're already seeing these galaxies form. And that's something that really needs to be explained.
If you can't see the Cephalonic stars in those distant galaxies, how can you accurately measure the?
Yeah,
distance?
well, there are other distance measurements. One of the distance measurements used here is that in the spectrum of a galaxy, the galaxies are, and there's a cutoff where hydrogen begins to absorb light. Because hydrogen is all over the universe, it's a strong absorber, but it has specific wavelengths where it absorbs. And that cutoff occurs at a certain wavelength in hydrogen, but that's shifted by the expansion of the universe, which we'll get to next time. And from that shift, you can get the distance.
So is that actually more accurate than the other?
No, I don't think so. It's and the tricky thing, of course, out here is also not only, you know, it's not an abrupt thing. So there's some error there. And also, this is somewhat model dependent, how you think the universe expanded. If it expanded uniformly during the whole time, then that would be an accurate distance measure. But if the expansion rate changed, as it has, then it gets more complicated. All right.
How is it determined that the whole galaxy rotates 230 million years? Like,
We can measure the speed of stars as they move. Okay.
So, Roger, if the Big Bang was about just 300 million, 200 million years earlier than
Yeah.
13.3, does that mean this is the earliest galaxy we have ever seen, and the rest is basically a big soup or whatever?
This is, we've seen hundreds of these.
Yeah. But we see.
And this is the earliest type we've seen. We are trying to push back even further. What is it?
Yeah, but the James Webb Telescope probably can see further than 13.38 million, but it doesn't see anything. So isn't that the conclusion that the
No,
may
that's
not
not
be-
right yet. We haven't gotten, that may be the way it ends up, but it's not there yet. We're still exploring all of those faint spots that we see and trying to see what the earliest ones are.
So
And that's a
the
big
next-
job.
That's the
See-
next
see-
telescope.
See, yeah, but even with the James Webb, see, when you want to push it fainter and fainter, that means you have to integrate longer and longer, take a longer and longer exposure.
Mm.
And that takes now, and that will be happening with the James Webb, but in its first 2 years, we're not sitting on an object for months at a time to see how faint we can get. But that will happen. That, I'm pretty sure they'll do something like that. See, am I going the wrong way? I think I'm going the wrong way. All right, let me just summarize here. Galaxies are vast associations of stars. This is what you need to remember. They're a major subject of current research. Lots of things we don't know about them. And they're the objects that we see at the greatest distances at the longest time, at the oldest times. Okay, so, and that will be it for today. Next time, we're going to talk about the expanding universe.
How long was that exposure for that?
For that, I don't know how long. A couple months, but,
Roger, I have a question.
yeah,
So each of those galaxies have millions of stars, billions of stars. And they all have planets, some of them have planets, and there must be, how many Ollie classes?
yeah, well, that is a scientific question, and it's a good one. And so far, we don't know of anything that's happened on Earth that couldn't happen elsewhere. Now, we don't know how common it is. We don't know when it started, when it starts in the universe. Those are scientific questions, and questions that we are dealing with, though. Before 1990, we only knew of one star that had planets, namely the sun. Now we know of 5,000 planets around stars. And the statistics are such that essentially all stars like the sun have planets. So there are billions of planets. So that's a big step ahead, because the one place where we know life does occur, may occur elsewhere, but the one place we know it does occur is on a planet. So knowing a lot of planets, that's a good place to look for life, right? So that is going way ahead. I was going to talk about this at the last lecture, but since you asked, it's an interesting thing. The next big project NASA is going to do is going to be a telescope that might be able to see evidence for life on nearby planets outside the solar system. Okay, and that's the Habitable Planets Explorer. I can't think of the acronym right now. But anyway, that's the next big thing that NASA has agreed to do in the last year. We don't know what the telescope will look like. It launches sometime in the 2040s. But that will be the next big thing after JWST. Eat your vegetables, okay? All right, thank you. What did I do on time? Oh, boy, I hit the time right exactly. I didn't.
So, we know that that star that we're, that's talking about is so many years of the formation. Does that now say that it was universe created before we think of it?
No, we
Have an estimate maybe?
yeah, we have a good estimate